Now we will start chapter 9, which is distress models in flexible pavement. So distress models means like the equations we use to calculate different kinds of distresses. So at the beginning we will start the first one, which is bottom of fatigue cracking. Now, so what our software does, software uses some equation to calculate the amount of fatigue crack. So now we will see how software does it. But before starting, let me tell you something that uh, using hand, very small amount of calculation can be done. Uh, because in real there are different kinds of wheel load. Like some are single axle, inside single axle there are different kinds of load. Some are tandem, some are tridem, some are quad. Even the temperature of the asphalt changes with time. Morning cold, after every half an hour, every 1 hour, the temperature of pavement changes. As temperature of pavement changes, the modulus changes. So many varieties in asphalt. We cannot do everything by hand, but we will learn in this chapter how to calculate. So this is an not example. This is the mechanism of bottom up fatigue crack. If there are like repeated load on the pavement, that will cause repeated tensile strain at the bottom of asphalt. And then after many repetition, crack starts and it reaches the surface and forms like this. That is a fatigue crack or bottom of alligator crack. And now we can calculate the percentage of this crack. How? We will see that. Okay, before seeing this equation, it will be it will look confusing to you. I'm showing it here. So let us NF. What is NF? NF is the fatigue life. Fatigue life means the amount of cycles the asphalt material can take. N is our actual number of load. Say our fatigue likes say 2 million. It's just an example to understand. Fatigue life 2 million. That means my asphalt material can take 2 millions load. Now if the actual number of loads say 1 million, that means 50% of my capacity is gone. So then we calculate DI, damage index. Damage index is just a number which is actual load divided by my capacity. Uh, that is called damage index. It is a fraction number. Say here 0.5. How 0.5? 1 divided by 2. So 0.5 here. Now this damage index doesn't tell that my pavement is 50% failed. This is just an index. Using this number, we can calculate the fatigue cracking, which is percentage of lane area. Whatever my lane area, we can calculate it using this equation. Now this equation is a long equation. We will see now how to find NF, or how do I know what is the capacity of my life. Yeah, this is a long equation. We will see it in our book. So let us go. So what this is, this DI, this is the damage index. Bottom means from bottom of fatigue crack. Here you can see N by uppercase N. Bottom means bottom of fatigue crack. What is JMLPT? It different kinds of variable. Say J means axial load interval. That means axial load. Okay, if I go to down, and then if you see M is axial load type, L is track type using class. That means different kinds of track. P means month, T means temperature. There are so many variables which we cannot do it by hand. We'll do by software, but here just to understand easily. Okay, so this is how we can calculate damage index. So we need to find NF. How to find NF? NF, there's equation, we can use it. So this equation is given here. Now it looks so confusing, but it is very simple because Kf1 is a constant, is given here. See Kf1 is here. What is C? C is 10 to the power m. What is m? There is an equation. So here everything will look confusing, but one by one you can find solution. M is this. Now what is VBE? You saw it in your asphalt material class. VBE is effective binder content. That means whatever the asphalt concrete asphalt binder we used in the mix. And what about the effective portion? That means the portion that is on the aggregate surface. Vm is air void of the mix. So using this we can find m. Once you find m, we can find c. We can insert c here. What is ca? Ca is a correction factor, a thickness correction factor. How to find it? There's an equation here. In this equation, on this only a is ma. What is a is ma? Thickness of asma layer, thickness of the asphalt layer in inch. If you insert here, you will get CAs. So now you can see everything is becoming very simple. So you got CA is beta A1. What is beta A1? Beta A1 is local or mixer specific field calibration constant. That means if you do not know anything about it, it's 1. Now, why our software kept us gave us an option for this? That means our local material may be different from other states. So my local climate may be different. So to account that, we have some option. That means, say for Colorado, this may not be 1. This may be 1.5, whatever. So there is an option for it. It's local calibration. You will know about this more at the end of this chapter. So if you do not know anything here is 1. Epsilon T bottom, that means whatever the tensile strength is developing and the bottom of the asphalt. That means if there is a load, if I apply some load here, some tensile strain will develop inside the material. That is tensile strain. Then E is the dynamic modulus of the asphalt concrete. Why do we need it? You can see here. That is the dynamic modulus of asphalt concrete. Now, what is this factor? Kf2. Kf2 is given here. Our software gave it. Beta f2. If you do not know anything, beta f2 is local calibration factor 1. Similarly, kf3 is given here. Beta f3 is given is a local factor, so 1. Now these factors may change anytime with the update of this standard. So now you are seeing this after 2 years, 1 year, 5 years. It may not be like this. It may change. So if it changes, do not think that it is wrong. Currently we are using this. It might change anytime. So this is the equation. We find the fatigue life for a particular type of strain and for particular type of modulus. Now, so if I go back to my other, so this is the way to find NF, and this is the N. You can count it actually. Then you can find damage index. Once you find damage index, you can find amount of cracking. How to find amount of cracking? You can see this equation in your book. 1/60 C1 star plus C2 star log DI. This DI is just we calculated. C1 star, C2 star, C4, all are factor. Everything is given here. You can see everything is given. C4 is 6000, C1 1, C2 1, C1 is 2, C1 2. So you can calculate everything here. Now, from this calculation, whatever you get is based on 50% reliability. 50% reliability. Now, if you want to increase our reliability, say 90%, 80%, whatever, then what we need to do? Whatever you calculated is based on 50% reliability plus standard deviation, standard error. How can you find standard error? Using this equation. 1.13 this divided by FC. Whatever FC you got it, then you can calculate the standard error. After finding this, it is then multiply by normal divide. You saw this in chapter 7 also. Normal divide. Say for 90% reliability, normal divide is 1.282. So there's a table here. You can calculate this. Then using this calculation, you can find the amount of cracking at any reliability. Okay, so now there's an example here. It's a short example. An asphalt pavement has the surface layer of 4.5 inch, base layer of 6 inch, sub base layer of 8 inch. What is the thickness correction factor? So thickness correction factor, there's the equation, you saw it. In this equation, this is ASMA thickness in inch. That is 4.5 here. Insert 4.5 here, you'll get a thickness correction factor. It's a simple example just to warm yourself. Okay, then another example might be a big example. An asphalt pavement has the surface layer of 4.5 inch, base layer 6 inch, sub base layer 8 inch, After 5 years of surface, the asphalt layer accumulates a bottom-up fatigue damage index of 4.5. That means DI. This is not cracking. This is index DI 4.5%. Then what is the amount of bottom-up fatigue cracking as a percentage of lane area after this 5 years? So simple. This is the equation. Everything is known. Only DI is given here 4.5%, but DI should be used as a fraction. You should not use percent. Okay, so if I go down, now they determine the factor C2 star, C1 star. They already calculated here, and then DI they inserted. You can see here it is a fraction number multiplied by 100, so they are using directly 4.5 here. After calculating this, they got 2.52. Now this calculation is based on 50% reliability. Whatever calculation we do, say the average age in a class, if I take the average age of all students in a class and divided by number, the average age is at 50% reliability. That means 50% people below it, 50% people above it. So the same thing here, it is based on 50%. Now to find it at certain reliability, what we need to do? We need to find standard error. How to find it? You saw this equation earlier. Using this equation, just insert here 2.52. Then if we insert it here, then whatever you will get is standard error. Then whatever is 50% plus error times the normal deviate. For 90% it is 1.282. Then we found 7.4, and this is at 90% reliability. Okay, so another example here is a big example, I think. Yes, alligator cracking. So an asphalt pavement has different kinds of load: single, tandem, tridem, quad. Annual load repetition is this. For this load, the tensile strength developed at the bottom of asphalt is this. Now these are some simplified. We assume that annually this amount of single axle will come, but it may change. And the dynamic modulus is 500,000 psi. Now it changes every second, but we are using average number so that our calculation is easier. Okay, then some other parameter given: year void, effective asphalt content, thickness of asphalt layer. After 10 years, what will be the alligator crack? What to do? Simple. First determine all the factors, then use the fatigue life equation. Okay, in the next page you can see fatigue life equation. After the inserted all the factors, the equation becomes this, where this is tensile strength, this is the dynamic modulus. Then using that table for each category, we will find damage index. So single actual load strength is this, E is this, NF is this. How I found NF? Using this equation. Then actual by capacity. That means this by this is this. This way we found the damage index for all. We summed up all. Multiply by 10. That means we are taking it after 10 years. Why? The problem is asking after 10 years. Okay, once we find the damage index, how to find cracking is this equation. Find all the coefficient. After finding all the coefficient, just you insert here the damage index in decimal. That will give you the amount of cracking at 50% reliability. Okay, you can see we inserted everything as we calculated, insert it here, and we got the amount of cracking after 10 years. So you can see here this process is not so difficult, but it is confusing at the beginning. And the example they gave us some simplified problem so that we can solve using hand. Now same problem again, similar problem. You can see annual repetition, tensile strength, and average modulus, but this time they did some changes. They changed the coefficient. What? You can see beta f1, beta f2, beta f3. These were 1 in the previous example, which are local calibration factor default value. But in this case, we are using some values that C dot Colorado Department of Transportation determined recently. Again, this might change at any time. because they are doing continuous research. So what is the difference between previous example and this? Only this. We will insert it in the fatigue life equation. Everything else will be similar. So if I go down, they found some coefficient of this fatigue equation. Then after inserting this, the equation is this. Then they calculated the fatigue life for defined condition. See, fatigue life for defined condition. Then actual divided by life is damage index. So they calculated damage index for all, summed up and multiply by 10 because they want after 10 years. After 10 years, and then they use the cracking equation. If this equation, they found the coefficient and insert the di, and then they found cracking. This cracking is at 50% reliability. Then what they will do, they will find at 90% reliability. How? They calculated the standard error, and they know the normal debit for 90% is 1.282. So 50% plus 1.282 times my standard error will get 21.96%, roughly 22%. That is a 90% reliability. 90% reliability means if I design 100 pavement, 90% pavement will satisfy this. Okay, so hopefully you understood one model. Then the next model is top-down longitudinal tracking. We will not go there now, but at least you learn how to calculate the amount of fatigue cracking in as per pavement. I will stop here. In the next video, I will um, uh, talk about the rest of the models. But again, before starting, it looks very confusing, but it is very simple. Thank you.